Hello friends, welcome back for another deep learning project, model translation using transformer. So here we will translate English language to Spanish language, and before proceeding to the implementation we will discuss about the architecture of the transformer. So to discuss, let's move to the notepad. So now we are in notepad. We will discuss on the architecture of transformers, which the transformer introduced in the paper Attention is All You Need, which revolutionized natural language processing by replacing recurrent and convolutional architectures with a model built entirely on self-attention mechanism. So what transformers are? It replaced recurrent and convolutional architectures, and it is only depends on self-attention mechanism. So transformers changed the whole world. These transformers are nowadays we are using, as OpenAI is using in GPTs, Google is using Gemini, and BERT, T5. All these models has this basic architecture transformers, so which we will be discussing now. And as we know, the recurrent layers like LSTM and GRU will have the capability to remember the word order, but in the case of transformers, as it relies only on self-attention mechanism, so we need to do some kind of positional encoding. And also we know that convolutional layers also have the capability of capturing the spatial dimensions, as we replace both recurrent and convolutional architectures by using self-attention mechanism. We need a positional embedding layer. As we know, the deep learning models will work only on numbers, not on the strings, so we need to convert the strings to tokens, then get the embeddings of the tokens, and from the tokens, as the transformers lack the word ordering, that's why we will do positional encoding. So transformer will contains architectures like the first one is token and position embedding layer, where we will have two layers, one for embedding the tokens, another for embedding the word indices from the vocabulary. That is nothing but position embedding. and the convention is to add both token embedding and position embedding. That's the first layer in the transformer. The second one is an encoder decoder architecture. The encoder is stacked n times, generally preferred 6 times. Then we will have a decoder which is also stacked n times. Then finally we will have an output layer, that is a feed forward network. That is a dense layer. So up to here, I hope you all are clear. So let's discuss what builds up the encoder and what builds up the decoder and what builds up the token and position embedding layers. Token and position embedding layers comprises of embedding layers, which is available in Keras. So the embedding layers will take positive input integers, then create the embeddings or generate the embeddings from those positive integers. Then we will have another position embedding, which is also takes the indices of the tokens generated from the vocabulary will be embedded. That is also done through the embedding layer available in Keras. Then we have encoder. So encoder comprises of 3 things. One is multi-head self-attention layer, another one is feed forward network, and the final one is residual connection and layer normalization. So encoder comprise of first one multi-head self attention layer. This allows each token to attend to all other tokens, so to capture different relationships. I repeat, this multi-head self-attention layer allows each token to attend to all other tokens to capture different relationships. Then we have a feed forward network which will be applied to each token. Multi-layer perceptron, it is also called as multi-layer perceptron. Then we will have residual connection and layer normalization. I hope you have the prerequisite knowledge like feed forward network, multi-head self-attention and residual, as well as layer normalization idea. And this residual and layer normalization is added around each sublayer to stabilize and speed up training. Then we have decoder, which comprise of masked multi-head self-attention layer, then we have multi-head attention layer, then feed forward layer and residual connection with layer normalization. The first is masked multi-head self-attention layer. This will prevent tokens from attending future token components, which is important for auto-regressive generation, because if the decoder sees the future tokens, then it won't work for inference models. That's why we need a masked multi-head self-attention layer. Then we will have a multi-head attention layer, which helps the model to relate input and output sequence. Then we will have a feed forward network, which is also called multi-layer perceptron, and finally we will have residual connection along with layer normalization. This is the decoder. Then we have the output layer. The final decoder output is passed through this layer, followed by a softmax to generate predictions. We will have a dense layer with softmax or sigmoid as per requirements. This is the architecture of transformers. So let's discuss the advantages of the transformers over other applications or models. The first advantage is that transformers process all tokens in parallel, which enables faster training, but which is not in the case of recurrent neural networks. So unlike RNN, transformers process all tokens in parallel, enabling faster training. The second advantage is that it is much better at handling long text or sequences than RNNs. Much better at handling long texts or sequences, then RNNs. Third advantage is that it will easily scales to billions or even trillions of parameters, and this is backbone for large models like GPT, BERT, T5, Palm and Gemini, etc. Easily scales to billion or trillion of parameters, backbone to large models like GPT, BERT, T5, Palm, Gemini, etc. And not only these are the advantages of transformers, these transformers also have some disadvantages. Let's discuss what are the disadvantages of these transformers. Then first one is the time complexity. If the sequence length is n, the time complexity is big of n square. So if we have a long text, very long text, then the model will be very slow. The second is input size. It will limit the input size because it needs large amount of data. Limits input size because needs large amount of data. And the last and important disadvantage of transformers is that even though the training is parallel, which I said here, even the training is parallel, the generation is sequential, token by token, which is very slow for inference. So even though training is parallel, generation is sequential, that is token by token, which is slower for inference. This is the architecture of transformers. Another thing I want to discuss on this platform is that we will be using Keras hub. The Keras hub is such a wonderful library which will provide us many layers, tokenizers, matrix losses to work with NLP projects. So we can build advanced NLP projects using Keras Hub, and for this case and this project we are going to use Keras Hub as it provides many layers. We will use different layers from it, and among them I will tell you some layers. That is the one layer which does this work, that is token and position embedding layer. We will have a layer for this. Then we have a transformer encoder layer for the case of encoder, and we have a transformer decoder layer for the case of decoder. This will make us simple to implement the transformer for the model translation work. So let's move to the implementation part. Decoder transformer. So first of all, we will import the required libraries like Keras Hub, Keras, TensorFlow, NumPy, Pathlib, and Random. The Keras Hub, Keras, TensorFlow are for building the model transformer, and NumPy is for numerical calculations, while Pathlib is to read the data files, and Random is for random generation of numbers. So make sure before starting this implementation you should have the accelerator GPU T4 times 2, and environment preference, always use latest environment. After that, to use the GPU as accelerator for our model, we are building a strategy through which we can use the GPU for accelerating the training of our model. So to build the strategy, we have a beautiful method, mirrored strategy, in TensorFlow, which will build the strategy for GPU connection, and using that strategy we can accelerate our training. And let's see the number of machines available in the system of GPUs, and which is shown using this print statement. And to get the number of cores or machines available in the system, we have an attribute number of replicas in sync, which is applied to the strategy. So here you can see number of cores is 2, that means we have 2 GPUs in the distributed system. After that, we are downloading and extracting a file which contains Spanish and English translated data, and that is available in this URL location, from which we are downloading the file name spa-ing.zip. It is a zip file, and from the zip file we will extract using the get file method and saving that file in the text file. After that, we are extracting the spa.txt file from the text file using the pathlib's path method. So let's extract. First of all, let's download, then extract, then move on to the spa.txt file, which contains English text and its translated Spanish text. So let's run it. So you can see the data is downloaded, and let's open the text file and split the text file between lines and save that lines in the lines variable. So all the texts are splitted, and let's see a few of lines from the lines. So here you can see it is an English sentence and its corresponding translated Spanish sentence is this. Similarly, it is an English sentence and it is the Spanish sentence. So we got 5 translated texts. So as it is in a text format which contains a /t separator, so we will change that to pair of text, in which the first will be a English text and the next one will be a Spanish text. So we will extract the English text and Spanish text and make a pair, and we will append that in this text pairs empty list. So first of all we will iterate over each line of lines, then we will split the line at the /t or tab space, then we will convert the English to lower and Spanish to lower case, then we will append that over this list. After that we are showing a random text pair from text pairs. Let's see that. So here you can see he married my sister. So its translated version is Él se casó con mi hermana. This is in Spanish. So after that we will split the text pairs into train, test and validation pairs. So first of all we will shuffle it, then we will reserve 30% of the data for validation and including test, where 15% will be for validation and 15% for test, and remaining 70% for training. So that's what we have done here. We are reserving 15% of text pairs for validation, and we are removing the 2 times of the validation samples from the text pairs so that we can get train pairs. That's what we have performed here. We are taking out the train pairs, validation pairs and test pairs, and this is a simple logic, and I hope you don't need to explain it. So let's run it. After that we are printing the total pairs, train pairs, validation pairs and test pairs via length method available in Python. So you can see total we have 1,18,964 pairs. Among that 83,276 is reserved for training and 17,844 for validation, as well as 17,844 for test. After this we will tokenize our English sentences and Spanish sentences. Before tokenizing we need a vocabulary. So for English we will generate a vocabulary from the corpus, and for Spanish we will generate a vocabulary from the corpus of Spanish data. So you might be thinking, what is corpus? Here the corpus means nothing but all the text pairs So the English text will be the corpus for tokenizer of English, and Spanish texts will be for Spanish tokenizer. So to get the vocabulary, we have a beautiful method in Keras hub, that is compute word piece vocabulary, which will return as a vocabulary from the data we provide to that. So that's what I have implemented, a function which will return as a vocabulary, where we will provide text samples, vocab size that we required, and the reserved tokens which we want to provide. So when we pass this to the train word piece method, first of all it will make the text samples to a TensorFlow dataset and save that in the word piece ds variable. Then using the compute word piece method available in Keras hub, we will create or generate vocabulary. So to that compute word piece vocabulary, we need to provide some arguments like data, vocabulary size, which these two are mandatory, and reserved tokens are optional. Reserved tokens are already defaultly 5 tokens are available, but in our case we don't need 5, we only use this 4 for pairing, for unknown, for starting and ending. So when we provide data, vocabulary size and reserved tokens, the compute word piece vocabulary will return a vocabulary for us, which is saved in the vocab variable, and we will return that vocab variable or vocabulary from the train word piece function. Let's run it. So let's generate the vocabulary for English, and also let's generate the vocabulary for Spanish. So to generate the vocabulary for English, we have to take out the English samples from the text pairs. That's what we have done here. From iterating over all text pairs and taking out the first text from the pair and making a list for it and saving that in English samples variable, which is provided to the function train word piece as a data English samples. Then we are generating around 15,000 vocabs. That means a maximum of 15,000 vocabs will be returned. So the vocabulary's length will be maximum of 15,000 only, or less than that. And we are providing the reserved tokens as these 4 tokens, and it will return as a English vocabulary. Let's run it, and it will take some time because it computes the vocabulary. Similarly, we will take out the Spanish text from the pairs and make a list of them and save that in the Spanish samples, and using the Spanish samples we will generate a Spanish vocabulary maximum of 15,000 vocabs, and we are using the same reserved token for this also. So let's run this. After that, we are just printing few vocabs from English vocabulary and Spanish vocabulary. So let's wait, the computation is under progress. it is computing the Spanish vocabulary, taking a while. After computing the vocabulary, we will use two tokenizers, one for English, another for Spanish. So yes, Spanish vocabulary is computed. Let's run and see the English and Spanish vocabs. So you can see these are some of the vocabs from English: at, know, him, there, hashtag, as, they, go, her, has, will. And similarly Spanish vocab: me, con, hashtag, as, que, li, la, ti, para, meri, las. So using the English vocabulary, we will create English tokenizer, and using Spanish vocabulary, we will create Spanish tokenizer with the method word piece tokenizer available in Keras hub. So let's run this and create these two tokenizers. So we have created successfully these two tokenizers. So the next step is to pre-process the tokens using the tokenizer. Or we will tokenize the text using the tokenizers. That's what we are processing here. And before doing that, we are packing out the sequence length with the tokens, especially the reserved tokens. And to pack that, we have a method start and packer, which will return as a sequence length with the padding value, start value, end value, and other reserved token values. So this is nothing but when we use this start and packer, it will convert the random size to a fixed size. For English case, we are converting the sequence length to 40 as fixed size, and we are just padding the sequence with the paired token, and we are converting the token to integer before tokenizing. And then for Spanish case, we have the sequence length of 41. That means this is the fixed length of the Spanish text. So first of all, we will have a start token, then we will have Spanish tokens, then if the length is less than 41, we will have a paired tokens, we will have some paired tokens. And if the Spanish translated version is ANDed, then we will have AND token. So the AND token will be between Spanish tokens and paired tokens. So we are doing this using the pre-process batch method, where we are providing two things. One is English, another is Spanish batch. So we are taking out the batch of, or we are taking out the batch size from the Spanish batch, then we are tokenizing English and Spanish text, then we are using the start and packer for both English and Spanish, so that the length of the sequence returned will be of fixed size. That's what the motto of start and packer. We are returning a dictionary of inputs and output. So in dictionary of inputs, we will have two inputs. One is encoder inputs, another is decoder inputs. The encoder input is English version tokenized one, and the Spanish one is this, and the output is this. So let's pre-process our text pairs and convert them to vectorized format. So it's done. After that, using the above mentioned methods, we will convert the text pairs and make them to TensorFlow datasets, pre-process them, then create a train DS, val DS and test DS. So in MacDS we are providing the text pairs, and we are zipping the pairs and splitting them into English text and Spanish text. Then we are converting English text to list. Similarly we are converting Spanish text into list. Then using the from tensor slices method, we are generating TensorFlow dataset and saving that in DS variable. Then we are batching with 64 elements in each batch. Then applying map method for pre-processing. Then we have a number of parallel calls equal to tf.data.auto-tune method. I have explained this why in many of my videos. And then we have shuffle applied to the dataset, and we are prefetching and caching and returning the dataset. So let's create this train dataset, validation dataset and test dataset using this MacDS method. Sorry, this is not a method, this is a function. And let's see the encoder input shape, decoder input shape and targets shape. So here you can see we have encoder input shape which is 64,40, that means batch of 64 examples, and sequence length is 40, and here also batch of 64 examples and sequence length of 40. We will provide two inputs and we will generate one output. So in machine translation you can understand like this: when we provide the first text, the machine should translate into some text in Spanish. Then when we provide another text, it should return the translated version of these two text. So when we give inputs or append inputs, then it will encode and also decode. That's why we have two inputs and a target. Target is the output translated sentence, while hidden states input is the decoder input, and the English text is the encoder input. After that, we have built a model and which follows the transformer architecture. So for that we will have a encoder input where shape is unknown, and you should have to give this name encoder inputs. This is mandatory. Then we are doing token and position embedding for this encoder inputs and getting the embedded features in the X So here we have vocabulary size 15,000 and sequence length 40 and embedding dimension is 256. After that we are having transformer encoder with intermediate dimension 2048, number of heads equal to 8. Here we will provide the encoded data and it will generate encoder outputs. So we have this model with encoder inputs and encoder outputs, that is the part of encoder. Now in decoder we will take two inputs. So the first one is decoder inputs and the second one is decoder state inputs. So do not get confused, just wait a while until I explain. So decoder will take two inputs, the decoder inputs and decoder state inputs. So we will embed the decoder inputs into X, then using the transformer decoder, see here, using the transformer decoder we will decode this X as well as encoded sequence inputs, that is this decoder state inputs. So these are the two inputs which is taken by the transformer decoder. So after that we are having a dropout layer where 50% of neurons will be dropped. Then we have a dense layer with 15,000 units with activation softmax. And here we will build a decoder with decoder two inputs, decoder inputs and encoded sequence inputs and decoder outputs as its outputs. And finally we will have a transformer outputs with this decoder inputs and encoder outputs. This encoder outputs is nothing but this encoded sequence inputs. I hope you understood. So you can see here the decoder inputs is the decoder inputs and encoder outputs is the encoded sequence inputs. That is nothing but this, its encoder outputs is same as decoder state inputs. I hope you understood. After that we are building the transformer where it takes encoder inputs, the first one, and decoder inputs, the second one, and the decoder outputs, this one. I hope you are clear, and this is what the transformer does. So let's run this and build our transformer. So the model is built under the function build model. Now under the strategy.scope we will compile the model so that we can use the GPU as the accelerator, and for this we are using Adam optimizer, sparse categorical cross entropy and matrix as accuracy. So sparse categorical cross entropy because we have integer values, and if the values are encoded into 1 hot, then you need to specify categorical cross entropy. So let's run this and compile the model. So model is compiled successfully. Now we will train our transformer model where we will provide a trained yes and we will train for 5 epochs. Then we will provide validation data as well, yes, and we have a checkpoint as callbacks. So the callbacks is nothing but it will save the checkpoints in the file path transformer underscore cp.keras, cp for checkpoints, and it will save the best model only, and the callback will monitor the validation accuracy, and when it goes maximum it will save in the file path. So let's train the transformer. After all epochs, our model reached to a training accuracy of 99% and training loss of 0.0244 and validation accuracy of 99% and validation loss of 0.01. Wow, great. So after this we will evaluate our transformer model with the test DS or test dataset. Let's try that. So the test dataset have only 279 batches, so it also returned 99% accuracy and 0.01 validation loss, test loss. So here now I am not building the inference model, and this is the task to all my viewers, that you have to build an inference model using this transformer model, and please put down a comment for that inference model. Thank you for watching this video. Have a great future.